Okay, hi everyone. Welcome to the last lecture of CS330 this quarter. Okay, so let's get into the content. So today we're really going to talk about some of the frontiers of multitask learning and meta learning, and talk about some of the things that don't work very well, or some of the things that are really on the fringe of the research that's being done, and some of the things that we could potentially do to fix some of these challenges. Great. There's also a question in the chat, a logistical question about whether we can use late days on the final project paper. Yes, you can use late days on your final project report. Okay, so in particular, in terms of what we're going to talk about today, first we're going to talk about meta learning for addressing distribution shift, for being able to handle, being able to quickly adapt to distribution shift by capturing equivariances and by adapting with unlabeled data to distribution shift. Then we're going to talk about multitask learning and meta-RL across very distinct task distributions, and what sets of tasks we might even train on, and some of the challenges that arise when you do this. And then we'll talk about some of the open challenges and open directions that we haven't yet talked about in the course. Okay, so first let's talk about addressing distribution shift. And first you might wonder, why should we care about distribution shift in particular? And for me, the motivation to look at distribution shift problems is that there's this gap between our current paradigm in which we study machine learning research and our current reality in which these algorithms are actually being deployed. And for example, in at least the realm of machine learning research, the way that things typically work is we assume that we have some data set, we train some model on a data set, and then we take that model and we evaluate it. And then we report some numbers in our research paper, and we're done. However, in reality, the world is constantly changing, from stock prices to supply and demand over time to robots exploring different parts of the world. What the observations that machine learning systems at any given point in time will change. What they're seeing will change, and the way that they need to make predictions will change as well. Rather than just deploying a static model that we can assume a static model will work as the world is changing. So we need to be able to think about how machine learning algorithms can handle the fact that the world is changing. Now, you might wonder, well, machine learning has been pretty successful in industry. How does industry cope with this sort of change? And one perspective on this that I think is quite useful is from Chip Huyen, who actually works on machine learning in production. And she has said that machine learning systems degrade really quickly because of concept drift. And for online machine learning systems, you want to update them as fast as humanly possible. So with this in mind, clearly the way that most machine learning techniques are being used is not the way that many of these research papers intended for them to be used. So what we'll talk about in the first part of this lecture is how we might use meta learning to allow models to very quickly adapt to distribution shift, rather than kind of the current paradigm in machine learning production, where you simply just take your model and fine tune it, for example, on all of the data that you've collected so far, and try to update them as you get more and more data. Okay. So now with this in mind, we'll talk about kind of two different ways to handle distribution shift via meta learning. And the first solution that we'll talk about is actually motivated by the fact that if you build in structure into your models, they'll be more robust to distribution shift. For example, if you build in the structure of convolutions into your model, then you're effectively telling your model that it should be translationally equivariant, at least for that part of the function. And therefore, if you then see data that's translated, then you can expect the predictions to be also translated, for example. Or if you use things like max pooling, if you see inputs that are translated, then the outputs won't change because it'll be translation invariant. And so this solution to distribution shift is great when we know what the structure is and how to build it in. Essentially, if we know how our distribution is going to change, like translations, then we can build in things like convolutions. But there are a lot of situations when we don't know how the distribution is going to change, and we also don't know how to build it in. So one question that we're going to think about in this first part is, can we discover equivariant and invariant structure via metalearning in a way that allows us to build it into the model and hence allow the model to generalize by kind of leveraging this sort of equivariant and invariant structure. Okay. Now, one question you might ask is, well, maybe metalearning algorithms already do this. And so we could take the MAML algorithm, which learns initialization, runs a few steps of gradient descent to get a new network. And one thing you might note is that MAML can learn equivariant initial features. So this initial network right here might exhibit features that are like have certain equivariant structure, like translation, like rotational equivariance and so forth, or rotational invariance. But the gradient update may kind of get rid of that equivariant structure. Equivariance may not be preserved in that gradient update. So even if it learned initial features that are equivariant, the resulting network may not actually preserve that structure. Do you have a question?
Yes, I wanted to ask if there are any experimental evidence that MAML can learn equivariant initial features.
I don't know of any experimental evidence. I will show some experiments in a few slides after I talk about one way that we can fix this challenge. And it will actually show that MAML kind of struggles to capture equivariance, at least in the sense of this kind of second network, or kind of the resulting network having that certain structure. I was asking, can you explain why the gradient update might not preserve equivariance? So I guess the kind of what I mean by it not preserving it is that like the gradient update is like even if it learns a set of features, for example, at this layer that like has a certain that preserves some sort of like equivariance property, that if you update the entire network, that's going to update other parts of the features. And if because like gradients, especially gradients with small amounts of data, have a lot of noise in them, it may be difficult for MAML to arrange its initial parameters in a way that allows this this gradient update to essentially preserve those features in such a way. I also think that the answer to this question should be a little bit more clear as we talk about a solution for solving this sort of this problem. Okay, so in particular, if we want to solve this problem, one thing that we could try to do is decompose the weights of this network into an equivariant structure and some corresponding parameters that are disentangled from this equivariant structure. And if we're able to decompose the weights in this way, then what we could do is only update the parameters in the inner loop and retain the equivariance and keep that fixed in this kind of update process. Okay, so this may seem a bit high level and vague, so let's try to actually dig into how we might do something like this. And to do this, we can think about how equivariances are represented in neural networks. And in particular, let's just look at an example. So if you take the example of a 1D convolution, where you have some filter here that is kind of slid across the input image or the input X, then you get an output that looks like this. Now, it turns out that you can actually represent something like a 1D convolution layer using a fully connected layer. And what this looks like is something like this, where basically the weights of the filter are repeated in this weight matrix along the diagonal of the weight matrix, and the remainder of the matrix is 0. And it's not hard to see that basically this weight matrix implements the same exact function as the convolution here. By seeing that basically when you kind of take the dot product of the rows, each of the rows in the matrix by the vector x, you get the resulting output. So essentially you can view things like 1D convolution as a certain pattern in this matrix that tells you how you should share parameters within this fully connected matrix. Okay. So with that in mind, how might we try to decouple or decompose the sharing pattern, or which captures the equivariance and the underlying parameters A, B, and C? What we can do is we can reparameterize this weight matrix W, and in particular reparameterize it into first a vector of the underlying filter parameters A, B, and C, and a matrix that basically just tells you for each of the elements in this weight matrix which of these parameters or what combination of these parameters does that weight matrix value have. And so basically if you take the matrix vector multiplication of this sharing matrix and the underlying filter parameters, you get a vector of a bunch of weights, and then you can reshape that vector to have the matrix shown on the left here. So we're going to call this U and this V, and U can capture symmetries by essentially capturing how underlying parameters should be repeated or copied in your weight matrix. And V can capture the underlying shared parameters. Now, this one thing that you can note, I guess a couple things that you can note. First, this sharing matrix doesn't need to be binary. It can have real valued entries, such that it's not just picking one of these parameters. It can also like take half of A and half of B, for example. And then the other thing is that you can apply this to fully connected layers, but you could also apply this to things like convolution layers. The output of taking U times V is just a vector of parameters, and that vector of parameters could correspond to something that you eventually reshape into a fully connected weight matrix, or it could be something that you reshape into like a set of convolution filters, for example. And interestingly, it turns out that for this particular reparameterization of the weight matrix, you can show that theoretically this can directly represent a decoupled equivariant sharing pattern and filter parameters. And you can show this for all group convolutions with finite groups. I don't want to get too much into kind of the group theory side of things, but the kind of gist of this is that it could represent a number of kinds of equivariances, not just things like 2D convolutions and 1D convolutions. It could also represent certain forms of rotational equivariance, reflection, permutation equivariance, among a kind of a wide variety of equivariances, although not all equivariances. So there's also infinite group equivariances that this cannot cover. Okay, but beyond the theory, kind of the key idea is that we're going to reparameterize this weight matrix W to have one component that can capture symmetries and one component that can capture the underlying shared parameters. Now, once we have these reparameterized weight matrices, what we can do is in the inner loop, we'll only update the vector V, which are the underlying parameters, and keep the equivariance fixed. This is such that when we run gradient descent, we can kind of preserve the equivariant structure, or the weight sharing patterns that are captured by U, and only update the parameters. And then in the outer loop, we're going to learn both U and V. And this allows us to essentially try to extract or discover the equivariances that are present in a set of tasks. So kind of visually what this looks like is if this kind of red gradient is showing your inner loop loss, the inner loop loss in mammal, then when you compute this inner loop loss, you're only going to apply it to V. This right here, maybe I should pick a different color. This is kind of the pre-update where you're computing the gradient update. After you've computed the gradient update right here, you get the post-update model right here. And this post-update model only has the underlying parameters that have been updated. And then you'll evaluate this model. This is your train set, this is your test set for these tasks. Now, one important assumption here is that there are some symmetries that are shared by all of the tasks. And if all of the tasks share some kind of fixed set of symmetries, then the goal is for this procedure to be able to extract those symmetries in the matrix U. Okay, so we refer to this approach as meta-learning symmetries by reparameterization, or MSR. Are there any questions on the method before I get to some of the experiments? Okay, so yeah.
Why don't we update U as well?
Yeah, so we're not updating U in the inner loop because we want to be able to preserve, like basically to extract equivariance from a set of tasks and preserve that equivariance when we're trying to learn a new task. And in particular, if we have that equivariant structure and that weight sharing pattern fixed when we're learning a new task, then we should be able to generalize more readily from a small amount of data because the network itself is kind of capturing things like rotational equivariance, for example, and then should be able to generalize to rotated images.
Okay, thank you. Hi, so when learning the equivariance matrix, do we like impose any constraint on it, or like we just let it learn it by itself? Because like I see the example, you sort of have like some sort of structure that makes it preserve equivariance, right?
Yeah, I mean, in general, it makes a lot of sense, I think, to impose some sort of structure on the matrix, either in a hard way or in a soft way through like a regularization. In this work, I guess one thing that we did with U is because U is quite a large matrix, we experimented with different ways to represent U, for example, using a Kronecker factorization or a low rank factorization so that it has fewer overall parameters. But it's likely that there's actually a lot more interesting things that you could do there to try to impose certain kinds of regularizations on U to encourage it to discover equivariances and not kind of capture other kinds of structure.
Okay, thank you.
Yeah, and is asking, can you also talk a bit about what we mean by equivariance and how do we measure it? So if you want to be equivariant, say you have some function f of x that produces y, then maybe then you have this kind of other function that you want to be equivariant to, or that you want your function to be equivariant to. Maybe this is function g. Maybe this is something that translates the image, for example. What equivariance kind of means is that when you basically apply f to something that's been transformed by g, then kind of this will give you an output that corresponds to g of y. So it's basically transformed in the same way. And then invariance means that when you transform the input in some way, the function still outputs the same thing. It's invariant to those transformations.
Yeah, my question is regarding to the structure of U. So for the example that's presented here, it seems that U can be like quite sparse in nature. So can we leverage that structure to like maybe minimize the parameters of U, as you said, like you had like many parameters?
Yeah, so encouraging something like sparsity with like an L1 regularization could make a lot of sense. We haven't experimented with that ourselves, but I think that it could make a lot of sense in future work. And this work is very, very recent, as you might have seen. So it's kind of on the frontier and fringes of research.
Thank you.
Okay, so on the experiment side, we looked at a few different things. The first question is, can we recover convolutions from translationally equivariant data? And to study this question, we set up a fairly, like a synthetic experiment, or experiment with synthetic data, where we just took random convolution functions, random 1D convolution functions, and meta-learned across those set of 1D convolution functions, where each function corresponds to a different task. And what we wanted to see is if we took this method and used a fully connected layer, a fully connected network instead of a convolution network, if it could recover the same performance as giving the network the convolutions itself. And so in particular, if we take, if we kind of take these convolution functions and measure the mean squared error on held out tasks, what we see is that mammal with a fully connected network and mammal with a locally connected network both struggle to get good performance. And this is kind of what I was talking about before, where it isn't able to capture this sort of equivariant structure. It may be destroyed in that gradient update. Whereas mammal with the convolution network can obviously do quite well because the data is translationally equivariant. And interestingly, this approach, building on top of a fully connected network, is also able to do about as well as mammal with a convolutional network, suggesting that it's able to kind of recover the structure from the data and preserve that in the gradient update. And the other cool thing that you can look at is you can look at the matrix that's recovered by MSR, and you see a matrix that looks like this. That looks basically exactly like the kind of the ABC repeated over the diagonal of the matrix, showing that it did indeed recover 1D convolutions. Now, next we can ask, can we recover something better than convolutions in situations where our data isn't perfectly translationally equivariant? So if we have data with partial translation symmetry, for example, that's when that's shown in the results here when k equals 2 and k equals 5. And in particular, what I mean by k here is k is the rank of a locally connected layer. And if the rank is 1, then there's just one filter that's copied for all of the kind of locally connected parts of the network. If k is 2, that means there's 2 filters. And if k is 5, that means there's 5 filters. And what we see here is that mammal with convolutions isn't able to capture this well because it's trying to encode too strong of a symmetry. It's trying to encode full translation symmetry, whereas MSR is able to do well across the board because it's able to recover the symmetries that are present in the data. You could also look at data with other forms of symmetries like rotation and reflection. And in this case, we also see that MSR is able to effectively extract that image symmetry to do a lot better than mammal just with convolutions by actually extracting the rotation and the reflection symmetry. Do you have a question?
Yes. So is these experiments done in the few shot regime or?
Yeah, these are all done in the few shot regime, and this is showing performance, mean squared error performance on held out tasks.
So if you have enough data, do you expect the mammal with fully connected will be able to learn this task?
Yeah, so if you have enough data of the held out test task, then we would expect all of these methods to be able to do well because there is basically enough data to learn that structure from scratch on the test task. You would probably need considerably more data than the few shot regime because basically like a convolution layer has like significantly fewer underlying parameters than an entire fully connected matrix.
Thanks.
Cool, that's a good question. Okay, and then I guess the one thing that I didn't mention here is in this last experiment, we actually applied MSR on top of a convolution, a convolutional function or convolutional layer. Okay, and then lastly, I'll also mention an experiment where instead of trying to recover symmetries from the synthetic data, we're looking at learning symmetries from augmented data. And in particular, you can run a meta-training process that looks something like this. That's basically the same as your standard meta-training process, but instead of just passing the train and val set of each task as normal, you augment the validation set. And by augmentation here, I mean things like random crops, random scaling, lighting variation, and so forth. And then essentially train the model to be able to generalize to this sort of augmented data from an unaugmented training set. So you'll basically change your train test splits to have a normal train split and an augmented val split, and then run your standard meta training algorithm with this split. And essentially what this is trying to accomplish is baking data augmentation into the architecture or update rule of your MetaLearner. Cool, and then what we find is that if you first compare MSR with Mammal, you get kind of performance gains across the board by nature of being able to capture these equivariances from the augmentation into the training process. It also outperforms almost no inner loop, which just corresponds to Mammal just on adapting the last layer, which is nice because if you only adapt the last layer, then that actually allows Mammal to capture equivariant features, but only update the features on top, the weights on top of that. And then it's also able to perform slightly better or comparably to prototypical networks in the omniglot setting, but significantly better on mini ImageNet where things are a bit more challenging. Okay, so kind of one takeaway that MSR provides is that it really gives a framework for understanding the interplay of features and structure in MetaLearning and allows the network to fix the structure when you're trying to learn and only learn features that are specific to the task. And this idea of fixing some things and training other things may provide may allow us to kind of learn and capture things other than equivariances, for example. Okay, so capturing equivariances is one way that may allow you to generalize better from a small amount of data. Now I'm going to talk a bit about adapting to distribution shift in the setting where you don't have any labeled data. And so to start off this part, it's useful to think about what sort of distribution shift we're going to be adapting to. So in the previous section, we were adapting to distribution shift where the things that were kind of changing were kind of translations or rotations or other sorts of transformations on the data. In this work, or in this kind of part of the lecture, we'll talk about a kind of distribution shift that's a bit more broad than those kinds of transformations. And in particular, we're going to focus on what's called group shift. We're going to assume that there's a categorical group variable Z. This may correspond to different users or different locations or different times of day. And this sort of information can typically be derived from metadata in your data set. And then we're going to assume that the training data comes from this distribution where there's this distribution over the underlying group, and then your data distribution actually depends on that underlying group, and that your test data corresponds to this distribution where P of X, Y given Z is identical, but the distribution over this underlying group variable has changed. And this can capture label shift. It can also capture most forms of covariate shift as well. Okay, and then our goal will be to try to be able to adapt to this sort of group shift with only unlabeled data, with basically only X and without having any access to Y from this part of the test data. Yeah, this sort of setting also captures problems like federated learning, where you want to adapt to different users or different devices. Now, it's worth understanding what sort of approaches have been used for distribution shift in the past. And one very popular approach for handling group shift is called group distributionally robust optimization. The way that this class of approaches works is that you form an adversarial distribution Q of Z over your group variable, and then basically optimize for the worst case group during training. And so you're essentially trying to prepare for the worst kind of group that you're going to see at test time, such that when things shift, you'll still be able to perform well. And so basically you form this adversarial distribution, and you're going to be minimizing the loss over this worst case Z. The benefit of group DRO is that it can enable robust solutions. It's also less pessimistic than adversarial robustness, where you're trying to consider, adversarial robustness is considering really a much broader set of shifts, where it's not just shifts in this underlying group variable. The downside of group DRO is that it often sacrifices average performance in the process of trying to be robust. It tends to be somewhat pessimistic about what's going to happen in the future. And so what we're going to try to do here is to adapt to distribution shift, or to be able to handle distribution shift, we're going to try to use meta-learning in a way that allows us to adapt to distribution shift rather than simply trying to be robust to distribution shift. Okay. And so in particular, what's going to happen at test time is you assume that you have unlabeled data from your test subdistribution. For example, like a new user, a different time of day, a new place. One example that you can consider here is a handwriting recognition scenario, where you're given data from a new user of kind of handwriting data of just the inputs. And you want to be able to use these inputs to better recognize the handwriting of this user. So you take this unlabeled data, you adapt your model using this unlabeled data, and also infer the labels for all of the data points simultaneously. And one of the assumptions that this is introducing is that the test inputs from one group are all available in a batch at test time, or at least in a streaming setting where you're seeing things like one at a time, all from a single group, and you can kind of store the data that you've seen so far from that group to allow you to adapt to that on the fly. Okay, now one way that this is different from things like fine-tuning and meta-learning is that this data is completely unlabeled. You're only adapting to unlabeled data. You don't get any labels from this task or from this part of the distribution. Okay, so we'll refer to this as adaptive risk minimization. And the way that it works is you basically just construct different subdistributions of your training data. This will correspond to different tasks. And then you train for fast adaptation with unlabeled data to these different tasks or to these different subdistributions, where different subdistributions correspond to like different users, different times of day, and so forth. Now, you might ask, well, how do we actually go about adapting with unlabeled data? A lot of the algorithms that we've talked about in the course may not make that easy. So there's two things that we could do. One thing that we could use to use MAML, but instead of using kind of MAML with a standard loss function in the inner loop, which we can't do because we don't have labels to compute that loss function, we're going to actually learn a loss function such that when we adapt with that loss function on this unlabeled data, our parameters can effectively solve the task or solve the group. And so what this looks like is we have some initial parameters, some loss function network parameters, and our examples. We run gradient descent on our learned loss function, where this loss function has some parameters phi. And then the result of gradient descent is we get a model with new parameters, theta prime, and we run our examples through those updated parameters. And then another way we could adapt with unlabeled data is something more like a black box approach, where we take some neural network. This neural network takes as input the unlabeled examples, and this is fed into this gives you some context, and you could essentially view this as like kind of, this is dtrain for the test. This is X test. And this is just basically a neural network that takes as input the training data and the test input, just like a black box approach. The main difference is that dtrain only consists of unlabeled examples and doesn't have any labels. Yeah, so is asking, can you explain what is unlabeled here and what is labeled? So these examples here are unlabeled. So like the examples that you get from a new user are unlabeled. And then you're using these unlabeled examples to adapt to that user, the way that they write. And then you're also, you pick one of these examples in your train set. This is also fed in here, and you're predicting the corresponding label. You assume that you have labels for training this meta learner at kind of during meta training, but you don't have those labels to adapt at meta test time. Does that answer your question?
What are some parameters when you say we're learning the loss function? Is it parameterized?
Yeah, so the loss function has parameters itself, and this is essentially something that takes as input the prediction from theta and kind of outputs a scalar value, and then you take the gradient of that scalar value and backpropagate that into the parameters of the network theta. Okay. Cool. And then in the simplest setting, this this context C in this network can actually just correspond to batch storm statistics, where you're basically just computing batch storm statistics using when you pass in these unlabeled examples into your network. And this kind of essentially provides a way to adapt the network to this unlabeled data, or to essentially condition the network on that data. Okay, so now how does this kind of meta learning with unlabeled adaptation actually look like? Experimentally, we compared to empirical risk minimization, or just like standard training. We also compared to the group distributional robustness that I mentioned before. And then lastly, we can also compare to empirical risk minimization, but upweight the groups to the uniform distribution. And this allows you to essentially, like if some of the groups are underrepresented, then upweighting them to the uniform distribution will allow you to kind of do better on groups that are underrepresented. Then we'll also evaluate ARM, and we'll specifically look at kind of 3 different versions of ARM. One is adapting with a context variable. This is somewhat similar to like conditional neural processes, which is just a certain black box architecture. One is adapting using the batch storm statistics, which is also kind of an example of a black box architecture, but is only the kind of the way that it's conditioning on the data is through the batch storm statistics. And then this corresponds to kind of mammal with a learned loss function. Okay, so we can look at one setting is the federated extended MNIST data set. And what this corresponds to is you want to be able to predict be able to recognize handwriting of different users. And by extended MNIST, it actually contains not just numbers, but also like the English alphabet. Okay, and then we'll actually also compare it to kind of a recent federated learning method here as well. And what we see is the first, you kind of see a 5% improvement in average accuracy from being able to adapt with unlabeled data across, like kind of, you take the best one of these, it's around 80%, this is around 85%. And then what WC means is that we kind of see a 10% improvement in worst case accuracy. And in particular, what worst case accuracy is looking at is it's looking at your accuracy on the user in which you did the worst. And this is a useful metric because you generally want your users to have a similar experience. And if you have some users that you're doing terribly on, then they probably, they might quit the platform or whatever, or they might not be very happy. or it's kind of unfair to that user because the model isn't doing very well. And this worst case metric gives you a sense of kind of how fair things are for the users and how well you're able to treat your treat kind of minority users and so forth. And so this 10% improvement is pretty substantial. Yeah, and then is asking, is BN learned or just calculated from the unlabeled data? So the statistics are just calculated from the unlabeled data. The critical thing though is that, and the thing that makes this different from just like standard neural network training with batch normalization, is that you're actually training it such that like when it gets a batch of data from a certain group, those batch norm statistics allow it to adapt to that part of the distribution. And so essentially what we're doing here is when you sample batches during training, you're actually sampling the batches to be correlated from a certain part of the distribution. And then you're also assuming that at test time, you're given a user and you're given a batch of data from a single user rather than a batch of data from like all users. And pointing out, it seems like it performs as well as learned CML or learned loss. So you're kind of still meta learning it such that when these batch norm statistics are computed across the examples, it does well. So you're still kind of have this meta training process. I guess the big thing that's different is that like in CML, it's actually learning what this context should be, whereas in batch norm, with batch norm adaptation, that context just corresponds to an average set of activations and the variance of those activations. By manipulating this network, it can actually kind of choose what it wants its activations to be, such that those statistics are informative of what part of the distribution it is in. Yeah, and then it's asking, why do we need CML and learn loss, which is more complicated? I think there may be some settings where CML performs better in, I guess there were like at least one example in the paper where BN was not the best performing method, but in general, it does seem like this kind of approach is the simplest and also works quite well. So it's probably what I would recommend. Okay, and then we can also look at a qualitative example. So if you were given this image right here, it's ambiguous whether this is like a 2 or an A. And also actually in this data set, in general, numbers are kind of overrepresented compared to characters. And if you just train ERM on the entire data set, it tells you that it thinks it's a 2. If you give the model just these 2 examples from that test user, then you think that it's kind of also a 2 because this doesn't tell you that much. But if you give the MetaLearner kind of all of these examples, then you could actually see examples like this, for example, suggest that the user writes 2s like this, and or like this, for example, and not like this. And that allows you to actually to adapt your classifier to this particular user. And by kind of adapting with these 50 examples, it can successfully classify this as an A. Okay. And then kind of one more experiment that's a little bit more kind of larger scale is you can look at CFAR-C and Tiny ImageNet-C. These correspond to basically a variety of different kinds of corruptions to the CFAR dataset and the Tiny ImageNet dataset. And the goal here is to adapt to new image corruptions after kind of training on different other forms of image corruptions. So we train on 56 corruptions and then test on 22 disjoint corruptions that weren't seen during training. And what we see is that we see a 3 to 10% improvement in average accuracy. So about 3% improvement on Tiny ImageNet-C and then about a 10% improvement on CFAR-10C. And then in worst case accuracy, we actually see a much larger improvement. We see an 8 to 21% improvement there, which is pretty substantial. Is asking what loss does CML learn in this case? So the black box methods aren't learning any loss. they are kind of adapting by just feeding the data into the network. Okay, so kind of the takeaways from this part of the lecture are, first, kind of preliminary evidence that meta-learning can capture equivariances by reparameterizing the weight matrices. And second, by allowing, we can allow adaptation and fine-tuning without any labeled target data by actually training for this sort of adaptive risk. So these are, I think, two promising approaches for addressing distribution shift and being able to very quickly adapt when the distribution is changing. Okay, cool. And then the second part of what I'd like to talk about is, what does it take to run multitask and MetaRL across distinct tasks? So first, when thinking about really like distinct task distributions, one thing that I think is useful to think about is like, have we accomplished our goal of making like policy adaptation, for example, very fast and effective? Can we now, like with the meta-learning techniques that we've talked about in class, can we now enable a robot, for example, to learn a completely new task really quickly after learning a wide variety of previous tasks? And I would argue that like a lot of the examples that we've seen so far in class allow the policy to adapt quickly to small variations on what it's seen before, but not really kind of allowing policies to adapt to completely new tasks that we haven't seen before. And if we wanted to adapt to entirely new tasks, one of the challenges is that we need our meta training task distribution and our meta testing task distribution to be like roughly the same. And if we need our task distributions to be roughly the same, and we want to adapt to entirely like distinctly qualitatively new tasks, then we're going to need a very broad task distribution such that when we kind of train on this broad task distribution, something that's like a distinctly new task still kind of generally falls under that broad task distribution. So we need a broad distributions of tasks for meta training. We also need this distribution to not be completely sparse, such that we can at least expect generalization within this broader distribution. If you think about it in the context of MetaRL, where might we get kind of a broad distribution of tasks? There are a few options. So there's things like OpenAI Gym, which have different continuous control problems. There's also the Atari learning environment, and there's this kind of surreal benchmark of different robot tasks. However, these different benchmarks aren't particularly well suited for meta-learning. So things like Atari, for example, don't have a lot of common shared structure between them. They're quite distinct. I think you also mentioned this on Monday. The same thing with kind of OpenAI Gym. These are kind of very sparse and distinct tasks that wouldn't necessarily allow generalization to a completely new agent. And for this last paper, there's only like around 6 tasks, I think. So we won't necessarily expect the ability to generalize to a new task or be able to quickly adapt to a new task when only meta training on 6 tasks. So with this in mind, we wanted to create a benchmark that kind of captures a large number of qualitatively distinct tasks that have shape reward functions and success metrics, and critically have some sort of shared structure, such that we can potentially expect generalization across these environments and tasks. And so the way that we did this is we tried to unify a state and action space across all of the tasks. And this was the result of this effort. So this is the MetaWorld Benchmark. It has 50 different tasks. I mean, it basically satisfies each of these desiderata with the hope of enabling or allowing us to study whether MetaRL algorithms can leverage these very broad and distinct task distributions to generalize to completely new tasks that you want the robot to do. And so now if you run meta-learning on these algorithms, meta-learning algorithms seem to struggle. So if you evaluate them on held-out-meta test tasks, their success rate is only around like 20 to 30%. And it turns out that even like they're kind of struggling on meta test time, but they're also struggling on the meta training tasks. So this suggests that it's having trouble kind of even learning to learn the set of tasks that is given during meta training. And so further, this kind of suggests, well, maybe we should just look at multitask learning. If we can't learn the set of tasks themselves, then meta learning may also be quite difficult. So if you kind of evaluate multitask RL algorithms on these, you also see that these algorithms are struggling to get like even above like 35%, for example. Okay, so why the poor results? First, maybe it's an exploration challenge, but we made it such that all the tasks are individually solvable. Maybe it's a data scarcity challenge. However, all the methods were given a budget with plenty of samples. And maybe kind of a limited model capacity issue, but in this case, all the methods were given plenty of model capacity. And it turns out that actually just training models independently on all of the tasks actually leads to a better success rate than if you try to train with soft actor critic on a single model and policy on all the tasks. So this suggests that it seems like that there must be kind of an optimization challenge when you try to train across all of these tasks, by nature of the fact that kind of independent training does better than if you try to share weights.
I have a quick question. I was just wondering, because of the link to my project, how do you measure model capacity? Because we haven't studied the context of overfitting in meta learning. We claim that these things won't overfit. So how do you measure model capacity, and also how do you measure plenty of samples?
Yeah, I guess I think that it's hard to measure these sorts of things. In this case, for model capacity, we tried making the models bigger, and it didn't help. So that suggests to us that they had plenty of capacity. And in terms of data scarcity, what we see here is that even kind of a multitask train, even a multitask policy levels off. And even if you give it kind of more environment steps, it doesn't continue to improve.
Okay.
Okay.
I'm still confused about why the task can be learned individually better than learning with MAML. So speaking of MAML, we have the inner loop, which I think is almost exactly the same as learning from scratch using such a self-actor critic method.
Yeah, so in this case, soft actor critic is just that this SAC corresponds to a policy and a critic that is conditioned on the task ID and trained to perform all of the tasks. So this doesn't correspond to MAML, although I showed MAML results on the previous slide. In principle, with MAML, you can, if at test time you kind of fine-tuned with enough samples, then it would like be able to do as well as independent. When we looked at that performance, that was with kind of a fixed budget of samples at meta test time. And here what I mean by plenty of samples is that's kind of the number of samples that you get during meta training or during multitask training.
By speaking of the samples, you mean the steps?
By samples, yeah, I mean the kind of number of environment steps or the number of episodes.
Oh, I see, thank you.
Okay. So given this optimization challenge, I guess the first takeaway here is that it does seem like training on diverse and distinct tasks shouldn't necessarily be taken for granted. It seems like when we move from tasks that have a lot of shared structure to tasks that are like much more distinct, then additional challenges arise. And second, one of our hypotheses about why we were seeing an optimization challenge was this hypothesis that maybe gradients from different tasks are conflicting in some way. And what I mean by this is that if they're conflicting, then they're kind of pointed in different directions, meaning that kind of one gradient wants the model to do one thing and another gradient wants the model to do another thing for two different tasks. And our second hypothesis is that in addition to conflicting, when the gradients do conflict, they cause more damage than expected. And in particular, what I mean by this is like, even if the gradients are conflicting, you should still be able to make progress on your multitask objective by averaging the gradients. However, there are some situations where you won't necessarily make progress. And in particular, if your objective has high curvature, then the amount of progress that you'll make may be a bit different. The amount of progress that you think you're going to make may be different than the amount of progress that you actually make. So we can look at a really simple example where you have this is your parameter, and this is your loss function. So this is like an example loss landscape that has a lot of curvature in the sense that it's not linear, it's kind of very curved. Say your current parameter setting is right here. And now say that your gradient, this is your gradient, this loss function is showing the gradient, the loss function and the gradient for one of your tasks. Now, if your gradient is telling you essentially to move this way, so it's essentially telling you that you should move kind of rightward to improve. And maybe this gradient is really strong, and there's another task that actually wants you to go in the opposite direction. Then if you end up ending up right here, when you had this kind of large gradient telling you that you should go right, then actually, sorry, I explained that a bit wrong. Let me back up a bit. So here's your current parameter update. Here's your gradient for one task. In general, this gradient is telling you that you actually want to go left because your optimum is to the left. And say you had another task that was cared very strongly about going to the right. Now, right here, your gradient is your gradient for the first task, for the blue task, is somewhat small. And so you think that, well, I'd like to go to the left, but if I go to the right, it's not terrible. But in reality, when you get this second, after you take the gradient update favoring the green task right here, then you actually end up in a spot that's much worse than you expected. So essentially this green conflicting gradient caused more damage than what your gradient was actually suggesting that it would cause, leading to a much worse loss value than what your average gradient was expecting. And then it's asking, is the damage caused by conflicts due to insufficient model capacity? I think that the relationship between model capacity and the landscape is a bit tricky. In general, it's I guess it doesn't seem like it's a model capacity issue, but model capacity can certainly play a role. And then is asking, can you explain why it's worse? So the reason why it's worse is that your gradient is just taking into account first order information, and it's not taking into account the fact that your function is curved. And so your gradient basically expects that if you take a step that is this size, that you'll end up right here. However, in reality, your function is curved, and so when you actually take this step, you end up in a situation that's much worse than what your gradient suggests. And this is something that happens whenever you have high positive curvature. Do you have another question?
Yes, so I just want to clarify my point. So I'm wondering, so if we have large model capacity, I think in this high dimensional loss space, we can find a direction where all the gradients, where the final gradient step move in the direction where all the gradient steps are taken to the right direction.
Yeah, so it's possible that this is less of an issue when you have over-parameterized networks, although in practice, we actually do observe that some sort of conflict or some sort of issue arises even with deep neural networks.
Okay, thank you.
And then it's asking me, this is true even without conflicting gradients. So yeah, high curvature is a thing even if you don't have conflicting gradients. The issue here though is that when you do have two conflicting gradients, for example, one that tells you to go in the opposite direction, then this is kind of more of an issue because you end up needing to make decisions between different task gradients. And if those decisions are based off of your gradients, then you kind of may favor one of the conflicting gradients over another in a way that isn't kind of the ideal solution. Okay, and so kind of one solution that we can think about to addressing this is try to avoid, when you're kind of considering multiple gradients, try to avoid making other tasks worse when you're taking a gradient step. And this may allow you to kind of prevent this sort of underestimation of how bad things will be when gradients are conflicting. And in particular, the resulting algorithm is really simple. So if two gradients conflict, if their cosine similarity is negative, then project the gradient onto the normal plane of the other gradient and do this for both of the gradients. And this essentially prevents the kind of update from GI from hurting task J and vice versa. And if the two gradients don't conflict, then you can just leave them alone and they'll have some sort of positive transfer. And we refer to this as projecting conflicting gradients or PCGrad. And what we can see is that while kind of performance of multitask training is typically worse than independent training, when we use this sort of optimization technique, we actually see much better performance than multitask training and also better performance than independent training. Okay, and then we also see performance gains in multitask supervised learning settings such as CFAR and NYU V2 as well. Okay, I was going to go a bit into kind of a little bit more of the theory of why it works, but we're running a bit low on time, so I'm going to skip this. The takeaways, though, are kind of still the same. Scaling to broad task distributions can be quite hard, and it can't necessarily be taken for granted. Training on broad and task distributions is kind of an important step in this direction, and it seems like there's evidence that addressing some of the optimization issues that arise from these broad task distributions can help a lot when you are trying to learn across these broad tasks. Okay, so now I want to talk a bit about open challenges. And in particular, we've talked already about a lot of open challenges in multitask learning and meta-learning through the course of this, over the course of this class. So what I'll talk a bit about today is just some of the open challenges that we haven't previously covered in this realm. So one kind of class of challenges is just addressing fundamental problem assumptions in multitask learning and meta-learning. So one area that we've talked about a bit, especially earlier today, is handling out of distribution tasks and long-tailed task distributions. And the reason why this is a challenge is that if you have a very long-tailed task distribution where different tasks correspond to like different objects or different driving scenarios and so forth, we know how to kind of generally do few-shot learning now, and this allows us to potentially adapt to this part of the data distribution where we don't have a lot of data or don't have a lot of labeled examples. But these few-shot tasks in this part of the distribution may be out of distribution. They may be from a different distribution than the kind of the parts of the distribution where we have a lot of examples. We've seen some kind of evidence that meta-learning algorithms can allow us to generalize to the tail. So one example that we saw early in the class was the prototypical clustering networks for dermatological diseases, which allowed for kind of some success on long-tail distributions. Today, we also saw adaptive risk minimization, which allows us to adapt to different parts of the distribution as well. But I think that there's still kind of a lot of work to be done here to think about how we might handle out of distribution tasks. And I think that further hints might come from the domain adaptation literature and the robustness literature to think about how we might adapt to things that are out of distribution. Beyond generalization, another kind of fundamental challenge is multimodality. So humans, for example, when we kind of leverage previous experience, our previous experience isn't always in the form of a set of tasks that we're given. We often have kind of rich sources of previous experiences that include visual imagery, tactile feedback, language from reading, and also social cues. And humans have this ability to kind of merge all of this rich previous experience in a way that allows them to build knowledge and use that knowledge to solve problems. And so kind of an interesting challenge for future algorithms is to try to learn priors across these multiple data modalities. This involves solving challenges such as varying dimensionalities, varying units. They also carry different and complementary forms of information. Some hints here might come from the literature on multimodal learning, but I think that there's still a lot of kind of interesting challenges that come up here. And one kind of interesting paper that is quite recent that starts to study this is this paper here by Liang et al., Learning in Low Resource Modalities via Cross-Modal Generalization. And then finally, one open challenge also is understanding when multitask learning will help and when independent training is just like the right solution. We saw one example today where independent training is actually sometimes actually quite a good solution. And it's helpful to understand when that's a good solution versus when different multitask learning techniques might be helpful for actually allowing better transfer across tasks. Beyond addressing these different problem assumptions, one open challenge is in this kind of field is developing and handling different benchmarks. So ideally we want benchmarks that show breadth, that really challenge current algorithms to find the common structure among those tasks and leverage that to learn more quickly. And also we want benchmarks that are realistic, that reflect real world problems that we care about. I think that there are steps towards some good benchmarks, such as metadata set, such as the MetaWorld Benchmark I talked about today, the Visual Task Adaptation Benchmark, and the Taskonomy dataset. And kind of a lot of these do have some reflections of real world problems, but ultimately we want benchmarks that, other benchmarks that study problems beyond like robotic manipulation and computer vision that have an appropriate level of difficulty and are also easy to use. We also saw kind of other benchmarks in class. So we saw kind of the land cover classification task. We saw the kind of the drug discovery like task where you're predicting the activity of different molecules. And these could also make promising benchmarks in the field, although so far I think they were primarily introduced as an interesting application and not necessarily as a benchmark itself. And then beyond kind of fundamental problem assumptions and benchmarks, there's also certainly room for improvement on improving the core algorithms themselves. This includes things like computation and memory, so making like bi-level optimization more practical, developing more of a theoretical understanding of the performance of these algorithms. There's actually been a fair amount of work very recently in the past year or so that has started to develop kind of some interesting theoretical insights on these algorithms, but there's still a lot more work to be done there. And then also kind of another challenge specifically in the reinforcement learning setting is in not just performing lots of different tasks, but also performing tasks in sequence, where you want to kind of compose different tasks that you've learned into longer horizon behaviors. And then also beyond these, of course, there's also the challenges that you discovered in your homework and your final projects, which I'm sure there are multiple. Okay, so those are some of the challenges that I wanted to highlight. Before we finish, I wanted to end on kind of a bit of a broader note and touch back a bit to some of the things that we talked about in the very first lecture. So in particular, if you think about the biggest advances in AI and machine learning and kind of what the biggest milestones have been in those areas, they've been things like TD Gammon or IBM Watson with Jeopardy, or kind of machines that can translate between languages, or things that can play like Atari games or play Go. And I think that all of these kind of big milestones are examples of machines that are actually very specialized to solve like one task very, very well. And as a result, they kind of appear very impressive because these are things that might be very difficult for humans. So while impressive things may kind of appear potentially very intelligent, it seems like there's still things that are missing to get to the level of what humans are able to do. Humans are kind of able to do many, many more things than what our current machine learning and AI techniques are able to do. And I think that, like, in general, we've covered a lot in CS330 to make steps towards these kind of more generalist systems that can learn multiple tasks, that can leverage previous experience when learning new things, learning general purpose models of the world, preparing for tasks before you even know what they are, for things like skill discovery and unsupervised metalearning, performing tasks in sequence, and also being able to kind of learn continuously with lifelong learning. Now, what's missing? It certainly seems like these ingredients are things that are helpful for taking steps towards more general machine learning systems, but it's likely that this isn't kind of the full list of what we need to actually make kind of really significant progress in this area. And so hopefully now that you've kind of learned a lot of material in this course and that are equipped with kind of an overview of all of these topics, you'll have a better sense of figuring out exactly what's missing so that you can also make progress in this area of AI research. Great, that's it. A couple reminders. The final projects are next week. The schedule is on Piazza. The final project report is due at the end of next week as well. And this is also the last lecture. That gives you kind of 5 minutes at the end to fill out course evaluations. Please do fill out course evaluations. As this is still kind of a relatively young course, we really value your feedback. Your feedback during the mid-quarter survey was already extremely helpful, and we're planning to incorporate that into future iterations of the course. I'd encourage you to take the time to do course evaluations now, but I'm also happy to answer other questions as well beyond that. Any lingering questions?
So just thank you so much for the course. So you just skipped the theoretical part of the conflicts of the gradients. Can you quickly go over that? So I'm still a little confused about that.
Cool. I'll spend a few minutes to go through the theoretical part of PC Grad. So the first part that isn't theoretical, that's actually more empirical, is that you can take PC Grad. PC Grad is actually changing both the direction and the magnitude of the gradient, and you can just kind of ablate these two components. And what you see is that actually kind of, it seems like both of these two components are helpful, but actually changing the direction is more helpful than changing the magnitude. But getting back to kind of what we were talking about before, it seems like there's three properties that are like that are kind of maybe arising in multitask learning in which PC Grad might be helping with. The first is conflicting gradients. The second is large positive curvature. And the third is having a large difference in the magnitude of gradients for different tasks. And if you have these if these three properties kind of arise all together, which we kind of refer to as the tragic triad, then you could actually show that PC Grad actually kind of does better than just taking the average gradient. One quick illustration of this is like, here's one optimization landscape, and you could show that Adam gets stuck in this optimization landscape right here. It doesn't end up getting to the optimum, whereas Adam with PC Grad is able to get to the optimum. But but kind of more theoretically, we can show that kind of theoretically that if you have a large enough conflict, curvature and gradient magnitude difference, that for 2 tasks, then you can show that PC-grad is provably better than just taking the average gradient. I don't want to go too much into the details, but basically these 3 conditions kind of translate into these three conditions up here. And then you can show that basically the result of the PC-grad update leads to a better loss than the result of the multitask gradient. And then we can also kind of empirically observe that in practice, there seems to be large positive curvature, and the kind of conditions A and B seem to also hold most of the time.
So can I ask a quick question?
Yeah.
So from my understanding, then the loss landscape is the same, whether with or without this PC-grad.
The loss landscape does seem to be similar with and without PC-grad. PC-grad really isn't changing the loss landscape itself. It's changing how you apply gradients to the network from this inside the loss landscape.
Okay, so PC-grad helps to prevent some kind of local optimums by kind of decrease the conflict gradients.
Yeah, I'm not sure if it's exactly necessarily like a local optimum per se. It seems like it may actually be something that's a bit more like thrashing, where it's kind of getting a large gradient update for one task and then getting a large gradient update for another task. But yeah, you can kind of think of it something like that.
Yeah, I see. Because from your last slides, you are arguing that the Adam optimizer can get stuck at some local optimums.
So we observed that in this really simple 2D example where Adam got stuck here. It's harder to visualize like the loss landscapes of really high dimensional systems. So it's hard to understand exactly if that's what's happening in the deep neural network case, but we did observe that in this 2D example.
I see. Thank you so much. Thank you for the great class.
I have a quick question. I was wondering, so in conventional optimization, like convex, non-convex optimization, we can't optimize through an if-else loop. Are we able to do that through in backprop and in machine learning, deep learning?
So you're saying, sorry, in convex optimization, there's an if loop, an if else?
No, I mean, so you said here that if gi.gj is negative, then you take the normal planes of, I don't know what the operation is, but you project gj onto the normal plane of gi and vice versa, and then you take that as your gradients gi and gj going forward. But I feel like you definitely might break the graph into 2 hypotheticals in terms of gradient flow. So I was wondering if that's something that if the if-else loop there is differentiable, or how I don't know, maybe I should just go through the GitHub link or something. But I was just if you had any ideas on how you could implement something like that.
Yeah, so it's quite straightforward to implement because you don't. If it's not, this isn't like a meta learning algorithm, so it's just like a multitask learning algorithm, and you don't need to differentiate through the if and else. And if you did need to differentiate through it, that would be it would be a bit tricky. Although it might be, yeah, it would be a bit tricky. Although it's kind of like differentiating through a ReLU, which is like sort of tricky, but in reality it seems to be okay. Yeah, and I guess maybe the other thing worth mentioning is that you can actually show that in the convex setting, this does actually converge to the PC-grad does actually converge to the right answer. So it doesn't break like the convergence property of gradient descent.
Okay, thank you. Thank you for a great course as well.
Great, thank you everyone.